Hey, hi everyone, and welcome to the January MAPP webinar. Today's topic is Next Generation Climate and Earth System Models, Modeling at Fine Scales. Very excited about today's webinar. We have 4 speakers. We're going to start with Isaac Held at GFDL. He's joined in the room there by Olga Sergienko, also of GFDL Princeton. And then we're going to go over to Chris Bretherton at University of Washington, followed by Steve Kruger at University of Utah. Isaac's going to talk a little bit about GFDL modeling plans for its climate and Earth system model platforms. Olga, Chris, and Steve are leading 3 new climate process teams that were funded by the MAPP program starting last year, and they're in some initial phases of their work, so they're going to talk mostly about their plans for their projects. We're going to have a bit of a flow from kind of the GFDL point of view to the NCEP point of view as this webinar proceeds. Chris has collaborators from both GFDL and NCEP, and Steve has collaborators at NCEP. So that's the plan for today. We're going to do something new for questions today. Instead of unmuting the lines, which can sometimes be a little bit noisy, I'm going to ask that everyone submit a chat question if you have a question from one of the speakers. The way to do that is to go to the green bar on the top of your screen. If you hover your mouse over it, it'll drop down. And then you'll see a chat button, and you can send me, the host, a chat message. You can let me know you have a question, and I'll unmute your line, or you can actually type your question in if you'd like, and I'm happy to read it out. So please utilize that feature in order to submit a question. So without further ado, Isaac, are you on the line?
Yes, I'm here.
Okay, great. I'm going to transfer control over to your desktop.
Okay. Okay, welcome everyone. I want to try to bring you up to date a little bit on our development strategy.
Hi, Isaac. Before you get going, you want to hit the Share My Desktop button so that we can see your screen.
Share my... Hold on a second.
Sure.
Caught me by surprise there.
All right, looks good. Yeah, just go full screen with the slides, and then whenever you're ready.
All right, sorry about that.
No problem.
Can you hear me okay?
Yep, it sounds good.
Okay. Okay, we started a 4 or 5 year model development cycle at GFDL, thinking about what we want our next generation model for IPCC-like studies of centennial scale climate change, attribution, climate prediction. And just as a little background, in AR4, GFDL contributed quite a few models, which were an outgrowth, I'm sorry, for AR5. Our models were branches, a lot of models that were branches or outgrowths of our CM2 model that we developed about a decade ago. And there were quite a few branches. There was the Earth System branch that we call ES2M, ES2G, which is basically a carbon cycle built on CM2, although ESM2G used a different ocean model, an isopycnal model that's been under development here for many years. And then we also did some data assimilation, real decadal forecasts for AR5 using the CM2.1 model. We had a CM3 model, which had a very different atmosphere on top of the same ocean that CM2 was built on. That the focus of that development was on aerosols, cloud aerosol interaction, atmospheric chemistry, and also stratospheric dynamics. We went to higher resolution with the model we call HIRAM, atmosphere only for the most part, which we've used a lot, perhaps a dozen papers over the last couple of years, and also some AMIP simulations for AR5, typically 50-kilometer or 25-kilometer resolution. And we had a higher resolution coupled model. Our standard model at CM2.1 is roughly 200 kilometers in the atmosphere. But some of our higher resolution models are 50 or 25 kilometers. And we have a number of other models in the laboratory as well, which I will skip over here during my presentation, some of them much higher resolution. There's S.J. Lynn's work with global non-hydrostatic models, and we have high resolution ocean models that we think of as resolving mesoscale eddies in the ocean, CM 2.6, for example, with about 10-kilometer resolution. But those resolutions are somewhat too high for us to think of as being our trunk model for discussion of centennial climate change. But we do want to combine the strengths of all the models that we've worked with effectively into a new trunk model that we could then think of as sort of branching out in other directions as well, but it provides us with a core from which other development of GFDL would proceed in the future, hopefully. And so we started a new model development team last year, and this we think of extending roughly to the 2016 time frame. It's just, the goal is basically to develop the best climate model we can that we can use to study projections for several hundred years, attribution of the past century's climate change, and also prediction on seasonal to decadal scales. We want to try to keep that work unified in the long run with our climate change efforts. And keeping in mind we want to move to models that give us more information on regional scales from which we can infer climate impact. And we also want to run not just from concentrations of CO2 and aerosols, but we want to run from emissions. So we're talking about a model that contains both the carbon cycle and the atmospheric chemistry needed to predict aerosols given emissions. So that's sort of the flavor of the kind of model. The resolution from our experience and given our current computational resource, so we're planning, given roughly our current resource, and if that expands in the future, we can, believe me, we can adjust our plans to adjust to new resources. But the model that fits into our existing resources and that we can actually use for the kind of work we want to do is the resolution of 50 kilometers in the atmosphere and about 1/4 of a degree in the ocean. And we want this model to basically subsume the other models that we talked about. So it'll be developed into an Earth system model. It'll be based on a new ocean model that we call MAPP, which is itself combining the best ingredients of the two ocean models that were used in the AR5 study. And okay, so that's the target resolution. Just to emphasize that our work with the AR5 model, that higher resolution, has really raised the bar as far as what we expect from our atmospheric models. And one good example of that is simulations of global hurricane frequency and distribution. And our 50 and 25 kilometer models do very well at that kind of simulation, and we want to retain that. And that's one of our goals, is to retain that good simulation of hurricane frequency coming out of our new set of global models, so that everyone working with our trunk model has the advantage of working with a model that produces nice hurricane simulations. Something we've struggled with in the past, for example, I'm just giving a couple of illustrations, is the Madden-Julian oscillation. So if we take this model that produced that rather beautiful hurricane simulation, we look at the MJO, it's really disappointing. So we're working actively on improving MJO simulation in this 50-kilometer model. We're trying various convection schemes. We haven't settled on any specific scheme yet, but this is one example, work of Ming Zhao, where we do have a better MJO simulation. We observed on the upper left in model simulation time longitude correlations. And so we're happy with this. We're a little concerned that we don't really understand why the MJO improves the way it does when we change the model. And so we're spending quite a bit of time trying to understand why this happens, so we can hopefully retain it as we try to do other things with the model. For example, the convection scheme at present doesn't produce this particular convection scheme doesn't produce a very good diurnal cycle of convection over land. As we try to improve that, we don't want to lose the MJO simulation or the hurricane simulation. So those are the kind of things we're trying to understand. We'd like to a better feeling for why this improved. And this is just an illustration of the kind of science this new model will be able to address. We're incorporating all the aerosol physics and atmospheric chemistry from our CM3 model, and it's just a picture generated by Paul Genou, who works a lot on dust, showing in orange the dust simulation in the model. And this, again, is a model that produces fairly realistic hurricanes, so we can watch how dust interacts with Atlantic hurricanes. And we think that's an exciting area for the future that's sort of enabled by this kind of merging of our different modeling streams. Here's some of the challenges that we're facing. One is on the ocean, this a quarter degree latitude longitude ocean model is in a region where the model's not yet resolving mesoscale eddies, and some modelers think of this as kind of a no man's land where you don't get the benefits of going to higher resolution in the ocean until you get to something like 1/10 of a degree. A lot of us here don't agree with that. We think we can make this model work quite nicely, and I'll give you an example of that. But other things we're worrying about, of course, are aerosol cloud interactions. One of the major uncertainties in trying to do attribution of 20th century climate change. And there's a tension, frankly, even within the lab, which is not too surprising, of how much do we want to focus on sort of a bottom-up, process-oriented perspective and trying to constrain this complex set of issues, and how much do we use top-down constraints? That is, how much do we use the 20th century record itself to optimize the model? And sometimes those two approaches point in different directions, so we're struggling with that. And there's a long-standing issue, which I think we'll probably hear about more from Chris, on atmospheric boundary layers and how they control low cloud feedback from the model, which then determine, to a great extent, the climate sensitivity. And so we're thinking about some other boundary layer schemes, and there's always software challenges, how to get better performance out of the model. And here's just an example of what we mean by an ocean model. It's in what we call this eddy permitting regime. I've taken this from one of Bob Hallberg's presentations, one of our ocean modelers, and just it's an idealized model that shows what currents in this idealized ocean look like as you move from 2.5 kilometer resolution, well, in this mesoscale eddy resolving regime, to coarser and coarser resolution. And so these are often referred to as eddy permitting. There's some eddies being generated, but they don't have realistic amplitude. And presumably they're not generating realistic mean flows when they interact strongly with those mean flows. But we have a variety of ideas on how to deal with this problem. I'll just mention one that Malte Jensen has been looking at in the last few months, where this is again a slightly different idealized turbulent ocean model, which has some topography, generates some, this is a mean stream function at high resolution. So we don't have time to worry about the details. If you go to much lower resolution, in a typical way we do that, we lose most of the flow generated by these eddies. But we have a simple scheme that, based on this idea of backscattering the energy which is being dissipated by the numerical model, that returns us to the very realistic-looking flow as compared to the very high-resolution model. This is just one of the ideas we have. There are several others that Bob and Alistair Adcock and others are working on, where we think we can manage this eddy permitting regime and produce a very nice coupled model, affordable model for us for the next few years before we can afford eddy resolving ocean models for all of our work. So final slide, this is sort of the timeline we have for this development. Well, last year we were supposed to be, I think this is more or less accurate, focusing on atmosphere model development in ANIP mode, meaning prescribed ocean boundary conditions, also focusing on MAPP code development. It's a lot of work merging our pre-existing ocean models into this single code that can handle a variety of vertical coordinates. And we've also done some exploratory atmosphere-ocean coupling, which is quite encouraging as far as ENSO variability in the model. And so in this current calendar year, we're going to be working more in coupled mode with alternative MAPP configurations, focusing still on our convection scheme and boundary layer in the atmosphere, but thinking more about our working in this eddy-permitting ocean regime and trying to figure out our best approach towards that. And then probably next year is when we'll start building up our Earth system model again. And there's a lot of work going on, interesting science with our existing Earth system model. And from experience, we can't really develop our carbon cycle, ocean, ocean and land carbon biogeochemistry models before our physical models settle down quite a bit. So we think probably in 2015 is when we'll start seriously looking at Earth system simulations with this new modeling framework. So I'll stop there. Is there any questions? Thanks.
Great. Thanks a lot, Isaac. So if there are any questions from WebEx attendees, please send me a chat message. Let me know, and I can unmute your line. In the meantime, are there any questions here in the room or perhaps at GFDL, anybody who's in the room with you, Isaac? Okay, I think Ken Mooney has a question here.
Isaac, sorry, is there a question in the room now?
Hi, Ken.
Isaac, is there a question in the room?
No, I think the people here know all this stuff. So.
Yeah.
Isaac, this is Ken Mooney. I was wondering how long GFDL envisions pursuing a two-model approach, one essentially a physical climate model and one an Earth system model. Do you envision at some time that those two efforts will be integrated into one model, or do you
we already think of them as being integrated. For AR5, we had a couple of Earth system models based on different ocean models, admittedly, but they were built on our CM2 physical climate system, basically. And so we think we've already integrated that. But it's just, in practice, we have to develop the physical component. We have to go quite a bit down the road of developing our physical atmosphere-ocean coupled system before we can usefully couple to carbon cycle and dynamic vegetation modeling, et cetera. But we feel that we're totally unified. It's just the development process might not look like that at first. But,
if you look at your website, it doesn't look like that either, because you do, in fact, display a physical climate thrust there and an Earth system model thrust there also. So it just leads to some curiosity.
So maybe our PR isn't adequate there, but we think of the Earth system modeling work as fully integrated with our physical modeling.
So I do have, Rick, yeah, go ahead.
Hello, Isaac, Rick Rosen here. Time didn't permit you to say very much about your land model, land surface activities. Would you care to comment on what directions you might be taking those?
Well, we have a lot going on there. We have a substantial land group, and we're in the process of developing what we call LM4, which is a new land model that will. Our LM3 model had dynamic vegetation and land hydrology that was fairly sophisticated, but we're moving on both sides of the land model, both the hydrology and the vegetation. And I think we have a lot of interesting ideas. I'm not a land modeler, as you can see from my answer. But
well, that's fine.
We think of it as the hydrology, for example. We're moving towards more of a tiling approach where we can take into account the subgrid scale variation of slopes, which give you relatively dry and relatively wet or swampy areas within a grid box, which helps you understand methane. It gives you a starting point for thinking about methane emissions, for example. And,
so, Isaac, we actually have a number of questions.
Some information on LM4 if you're interested, Rick.
Okay, thank you.
Isaac, we actually have a number of questions from folks who are on the WebEx, so I'm going to start with John Cortinas. John, are you on the line?
I'm on the line. It'll just be a quick question. Isaac, I was wondering, as you're looking towards this new, this next consolidated model, if you will, are you considering if this is going to be based on built on ESMF?
Balaji is shaking his head, not in any strict sense, no.
Okay,
do you want to add something to that, Balaji? It's something we think we can do, at least regarding the outer envelope of ESMF rather than the internal sort of handling of parallel processing. But the outer envelopes we can always create relatively easily so that users can pick up our models.
Okay, thanks.
Structure.
So I'd like to go to Jialin. Lin also has a question. Jialin, are you on the line?
Yes.
Okay, go ahead and ask your question.
Yeah, for the much improved MJO simulation, which convection scheme was used?
This is a new scheme. This particular integration is a new scheme that isn't discussed in the literature yet. It basically has a shallow plume and a deep plume. The shallow plume is very similar to Chris Bretherton's UW shallow convection scheme. Mm-hmm. And the deep plume has a different closure than the shallow plume. And as I said, we don't have, we're not quite ready for prime time here yet, I don't think. We'd like to understand better why this model is an improvement. It does seem promising in the sense we can retain our nice hurricane simulation. And so from the short integrations that we've done, looks adequate, maybe more than adequate. I'd say it's a relatively traditional convection scheme with basically two different closure for shallow and for deep convection.
So is the moisture convergence involved in the closure, or? No,
it's the deep convection is sensitive the way it's constructed to the relative humidity of the free troposphere, for example.
Okay. Okay, thank you very much.
Thanks, Colin. Isaac, one more question really quick from Jim Kinter. I'm just going to read this. This is from Jim Kinter for Shukla. He asks, you mentioned the fidelity of MJO simulation as one of the metrics for goodness of model. What are other metrics that GFDL uses? What is the priority among metrics?
Okay, that would take about an hour to, the way that works out is we have a development team. And in fact, we have various working groups that meet. They meet weekly. Many of them meet weekly. And it's basically the people in the working group have, the individual metrics of what they consider to be a useful model. I mean, some people in the group their research is focused on ENSO, and they wouldn't accept the model that had significant deterioration of our ENSO simulation. Other people are looking at aerosols, the vertical structure of our aerosols, or the MJO is interesting because, as we all know, it's sensitive to the convection scheme. So it really discriminates. Something else that discriminates with regard to convection is the Darrow cycle of convection over land. And so you look for metrics that discriminate between the kind of choices you're trying to make. But we don't go out at the beginning and make a list of metrics and say this particular metric gets 10% weight and this one gets 6% weight, and decide in some kind of quote-unquote objective way what the best model is. We fight about it and discuss what the pros and cons are of each model configuration.
Okay, Isaac, thanks a lot for answering all these questions, and the presentation was very interesting. We're going to move on now to Olga, who's also in the room with you.
Okay.
Hello, then, can you hear me?
Hi, Olga. It's a little bit faint, so if you can
I'll
maybe
get closer. Is it better?
Yeah, that sounds good.
Okay. So, yes, we have a climate processing team which aims to represent Calving and iceberg dynamics in global climate models. And the reason to focus on that topic is that Calving accounts pretty much half of the whole mass loss from ice sheets that exist on Earth at the moment. What this map shows is partition between melting and Calving for all ice shelves in Antarctica. The big circles for all different ice shelves. They represent the mass loss. The size of the circle tells you how much mass is lost, and the shaded part represents calving. Dark part represents melting. What's interesting, if you look at two big ice shelves in Antarctica, Ross 1, the Ross ice shelf in Ross Sea, you can see that the west part of it, it's 100% calving, and for instance, just a little bit east of it, it's east part of the Ross ice shelf, it's already 50% melting and 50% calving. Similarly, in the Weddell Sea, there is a huge chunk that accounts for calving and substantial part for sub-ice shelf melting. For the whole Antarctic continent, the partition is it's 55% calving, 45% melting, and it's pretty much similar for the Greenland ice sheet as well. So there is a really good need to represent that process and understand what's going on with calving in general. So unfortunately, calving and icebergs, they come in all different shapes and sizes. What's shown on the upper left picture, it's an example of a tabular iceberg. It's called Nathan because it's still attached to the Ross ice shelf. So it's about several tens of kilometers wide and about 100 kilometers long, and usually such big tabular icebergs calve twice per century. On the top right picture, it's the front of Jakobshavn Glacier. It's not very large, it's about 10 kilometers wide, but it accounts for about 10% of mass loss from the Greenland ice sheet total. And what's interesting, you can see that this is the ice front where my mouse is, but right next to it, it's a lot of little bits and pieces and chunks, maybe several icebergs about a kilometer wide. So it's absolutely different story compared to the big tabular iceberg on the top left. These bits and pieces and small icebergs, they calve pretty much every day, especially when it's summer season and it's quite warm, so it's on scales of days and months. On the lower right, it's a picture of Columbia Glacier in Alaska. It's very narrow, just 2 kilometers wide, but again, you can see a lot of little bits and pieces, about several hundred meters size in front of it. And finally, on the bottom left, it's an image after Larsen B ice shelf collapse. That happened in 2002. Larsen B, the size of the Rhode Island, completely broke and disintegrated in hundreds of little bits and pieces and big icebergs. But that doesn't happen too often. This ice shelf has been stable since last glacial maximum, so it's about 12,000 years. So this represents why there is no so-called calving law that can account for pretty much all processes that describe calving. On spatial scales, calving starts on very small spatial scales. It's the size of ice grains and start cracks. It's about millimeter to centimeter scales. A little bit higher on spatial scales, it's fractures and rifts. It's about meter to kilometer spatial scale. And moving on much larger scales, it's about tens, hundreds kilometers to the size of ice shelves. So this is like many order of magnitude in spatial scale. Similarly, on temporal time scales, it's the same story. Cracks propagate with the speed of sound in ice, so it's even less than 1 second. But small bits and pieces and tidewater glacier calving, it happens on the order of hours to days and seasons. And as I said, large tabular icebergs calve several times per century, and ice shelves, as we know so far, collapse roughly every 12,000 years. So during this project, we are going to focus on spatial scales that are relevant to large-scale ice sheet models and as well relevant to climate models. So it would be several kilometers and high and up. Similarly, we are not going to resolve all small cracks and propagations, so pretty much time scales would be order of days and seasons and up about like a century or something like that. Now, when icebergs calve, they don't melt right away where they calved, and they don't disappear and teleportate somewhere. They spend a lot of time wandering around, and what this map shows is a cumulative iceberg tracks for about last 10 years or so. So these tracks, they are composed from satellite images, so they resolve pretty large tabular icebergs, larger than 5 kilometers or so. And as of January 7, when I last looked at that database, the farthest, not southern, but farthest north was about 45 degrees south. So the farthest north iceberg that has ever been observed from Antarctic is about 30 degrees south. So they do travel quite far. And considering that large tabular icebergs at about several hundred kilometers, they have huge radiative effect on the top ocean layer because they are white. They have absolutely different albedo than the surrounding ocean. Also, while they drift and travel, they melt, meaning they release fresh water. That means they alter ocean water masses. On top of that, they're quite thick, meaning they sit quite deep, and they alter mixing and all other oceanographic processes that happening around these big tabular icebergs. Also, they're big sources of nutrients because they carry iron and other components that kind of got frozen into ice when that ice was on the continent. So all those processes are important to the ocean circulations, and it is important to take them into account. At the moment, the only IPCC class climate model that has any representation of icebergs is GFDL climate model, but there is a caveat with that these icebergs are smaller than 2.5 kilometers, meaning it is exactly the opposite what tabular icebergs are, for instance. And these small icebergs are represented as Lagrangian particles, meaning they don't have any horizontal dimensions. And what that means that they can pile up in one model grid cell and cover it completely, so the coverage of that grid cell may be much larger than 100%. So in that sense, we do need to start resolving horizontal dimensions of icebergs to account for all those processes that I described above. And finally, what we plan to do with this climate processing team is that develop Calving parameterizations that are suitable to, for large-scale ice sheet models and climate models. Really try to understand iceberg-ocean interactions and develop iceberg component for the ocean model that physically represents dimensional icebergs and account for the effects of icebergs on ocean circulation, water masses, and probably geochemical cycle as well. And to calibrate and develop those parameterizations and validate the models, we plan to compile all available observations to see how often all bits and pieces of ice fall from different places, both in Greenland and Antarctic, and to compile data, all available data sets that they're useful not only for this particular project, but contribute for the general use as well. And I'll stop here.
Great, thanks a lot, Olga. Are there any questions here in the room for Olga?
No, not really.
Any questions there at GFDL? So there is one question on the chat board here. So it's from Marjorie McGurrick. So Marjorie, I'm going to unmute your line now if you want to go ahead and ask your question. Are you there?
Yeah, I'm there. Hi, Olga. Back on the map where you were showing the where the calving bergs go, can you show us about where that research vessel was stuck?
Sorry, repeat it again, please.
Can you show the research vessel was stuck in the Arctic ice? Antarctic ice.
Oh, the one where it stuck, okay, yeah. It happened over here, somewhere there, but it weren't due to icebergs. It's rather due to really thick sea ice. Actually, there is a strong effect of the icebergs on sea ice and how sea ice dynamics changes with that, but the major reason was pretty much very thick sea ice that piled up somewhere over here.
Well, they say, the mariners say that, you know, the icebergs move with the currents because they have a very deep keel.
That's correct.
That icebergs move with the winds because they have a very deep keel, and sea ice moves with the currents.
No, it's all the way around. Indeed, icebergs have very deep keels, so they're pretty much insensitive to the wind forcing, so mostly it's tides and deep currents that affect big tabular icebergs. And those kind of block usual passages for sea ice to blow away and the way how sea ice usually moves around. So that's what the effect is. Sea ice is not as thick as icebergs, so it's about like maximum 3 to 6 meters, and icebergs are about several hundred meters, so they sit much deeper in the water column.
Marjorie, would you like to ask your second question also?
Yes, please. I wanted to ask if the parameterizations that you're looking at would be similar at both the North and South poles. And secondarily, does the age of the sea ice or the age of the iceberg show up in your satellite analysis?
Well, the age, I'll start with the second one. It's the same iceberg that calves. It's then tracked through its evolution, so you always know what the age of it is. And this map shows the compilation of all icebergs that were observed during the past 10 years. Indeed, we do aim to develop uniform parameterizations that it doesn't matter whether it's Greenland, Antarctica, or Martian ice sheets with whatever ocean is there, so it should be quite general.
Thank you.
Okay, thanks for the questions, Marjorie. There's another question from David Considine. David, are you on the line?
Sure. Hi, I was just interested in knowing what you plan on doing with the optical properties of the icebergs, or if you're planning on anything.
No, we didn't have a specific plan, but pretty much everything would boil down to radiative properties, meaning the albedo feedbacks and the albedo effects.
Right, but are you planning on incorporating or doing anything with that, and do you have a plan for that or not?
We will be working on the fact that albedo, the iceberg albedo, is significantly different than the albedo of surrounding oceans. That's pretty much as the first step. So, that's our plan, to look at those properties rather than optical properties of the icebergs itself. They do not change much when it's still ice or frozen snow on top of it. Indeed, there is a huge change when icebergs start to melt and they develop melt ponds on top, but it's a much smaller scale process, and I personally know how to deal with that. So there is a plan how to parameterize, for instance, melt ponds on icebergs, and that optical properties of changing snow would be accounted in those processes.
Okay, great. Thanks for the question, David, and thanks for the presentation, Olga.
There is one question in the room, so I'll...
Oh, sure.
Yes, sure.
Yes, wasn't clear to me, maybe you said it, but are the icebergs going to interact with the sea ice?
Yeah.
Olga, can you repeat the question for everybody on the line, please?
The question was why the icebergs are going to interact with sea ice. The answer is ideally yes, but I cannot give you a definite answer whether we will get to that point or not. So ideally, we would like to have that.
Okay, great. Thanks a lot, Olga. Chris, are you on the line?
Yes, I am.
Okay, I'm going to transfer control over to your computer now.
Are we ready to go?
Yeah, looks good. Whenever you're ready.
Okay, so I'd like to talk about the new cloud and boundary layer climate process team. This is actually one of two cloud and boundary layer climate process teams. The other one that Steve Kruger will talk about, and I think the intent is that they'll try and work together in a variety of ways. Our team is an outgrowth of a previous CPP that I'll also mention some results from. It's represented by Zhang Han and Ruiyu Sun at NCEP, by Chris Golas and Ming Gao at GFDL, by Joao Teixeira and Martin Witek at JPL, and by myself, Chris Jones and Peter Blasi at the University of Washington.
Chris, just try it again.
So, yeah, the goals of the CPP are building on our previous one to implement a moist EDMF scheme. I'll describe what that means later within the TFS model that improves both operational weather and coupled climate metrics, improves the global cloud climate policy of TFS, in particular when it's coupled to the MAPP, so as to be a prototype coupled forecast system, and to compare the clouds forecast in 0 to 5 day forecast of the TFS with forecast mode simulations using versions of the GFDL climate model, and that's where the collaboration with GFDL comes in. The reason GFDL is interested in this is that they still are, I would say, having some problems making their new club boundary layer scheme perform better than simpler schemes, and are also actually interested in whether some of the same methodologies might suit their needs as well. So as context, we had a 3-year CPP that involved some of the same players over the last 3 years. It was focused on the subtropical stratocumulus to cumulus transition, which is basically the descending branch of the Hadley circulation in subtropical oceans, because that's where we had observations. And in addition to the people participating this time, this involved co-workers at NCAR and also UCLA and Lawrence Livermore, in particular having to do with the CAM CESM model. But we quickly found that although it is indeed the case that GFS has issues with the stratocumulus transition, the broader picture is that GFS and the NCEP coupled forecast system have much broader issues. In particular, they have too little cloud and far too little cloud radiative effect almost everywhere, by almost a factor of 2. There's a problem in GFS due to neglect of the dissipation heating due to turbulent kinetic energy produced in boundary layer eddies. It causes it to lose about 5 to 10 watts per meter squared. There's the subtropical stratocumulus maxima are too far offshore. And if it weren't for the clouds, actually CFS plus the MAPP ocean model actually makes quite a good climate model in terms of traditional climate metrics. So we aim to do some model improvement work, and we got started on a number of things. I would say none of them have yet come to operational fruition, although some are getting close. So one thing, and I should also say that the philosophy of our approach was it's partly an educational approach to try and work with our collaborators at NCEP such that they are in charge of developing the new schemes and maintaining them and making them better and tweaking them and so on. So a lot of the development work that's actually being tested has gone on at least partly by our collaborators at NCEP. So in particular, a new unified cloud scheme was developed Right now, the GFS uses separate schemes for cloud fraction and the radiation computation and the microphysical computations, which is obviously undesirable. The new cloud scheme does increase global cloud cover and parallel forecast tests. Unfortunately, it also degrades precipitation scores in forecast tests, for reasons we don't really understand. We showed that the calving parameterization doesn't have enough entrainment and it precipitates too efficiently. And by making those changes, we also are able to increase the global cloud cover in the GFS. That unfortunately degrades tropical winds, as I'll tell you shortly. We added code to put in a TKE dissipation heating scheme led by Zhang Han at NCEP. And we then implemented what we call a dry EDMF scheme, and again, I'll talk about what that is shortly. These all underwent parallel forecast testing to see if they could beat the operational skill scores of the GFS. And none of them significantly affect the central skill score, which is the 500 millibar root mean squared error as a function of forecast lead time. But it has proved hard to improve all of the tropical winds, U.S. precipitation, and the clouds. So as long as forecast mode skill is the ultimate metric, so we're sort of still having some positive and some less positive results. However, a basket of moist physics test changes, including parts of the TKE dissipation and dry EDM versions of the TKE dissipation and dry EDMF scheme, are in pre-operational testing in GFS, which is sort of the next step of toward actual operational implementation. Just as an example of the kinds of trade-offs that we have found, this is a comparison of a case where we improved, at least we improved what we thought was compared to LES, that would be the cumulus parameterization. So by increasing the entrainment rate, by decreasing the precipitation efficiency, and made a couple of other changes. And we did then a series of parallel forecasts using the new run, which is called short run 2, and the control run. And here, the left panel shows the change in cloud cover between the runs, and red is an increase and green is a decrease, averaged over a week of 5-day forecast. I think actually 3-day forecast probably what's shown here. And what you can see is there's a lot of red indicating the cloud cover increased by a global mean of 3.6%, which is good. However, the winds, so the right panel shows the root mean square error of tropical winds. And basically red indicates an increase, and the horizontal axis here is lead time, it's not shown, and the vertical axis indicates height in the atmosphere. And basically there's a lot of red indicating that the changes actually slightly degrade the tropical winds. Not by a lot, but that's not desirable. Similarly, we tried what we call a dry EDMF scheme. So EDMF, which the eddy-diffusion mass-flux parameterization approach, is a form of boundary layer transport scheme which combines an eddy-diffusion term proportional to the vertical gradient of what is that's being transported, and a mass-flux term where we explicitly simulate updrafts with one value of the convective property and compare the updrafts to the mean state and predict a mass flux, and then the transport is proportional to the mass flux times the difference between those values of the quantity P. In dry EDMF, we transport dry thermodynamic variables, the potential temperature and the water vapor mixing rate. So there's no latent heating included in turbulent motions. This is actually somewhat similar in spirit to the current eddy-diffusion counter-gradient CBL scheme that's used within the GFS. So this makes it easier in the sense that the scheme doesn't do things very differently, but on the other hand, it has the problem that it can't mix through moist adiabatic cloud layers such as stratocumulus. And so as a result, it tends to under-deepen the boundary layer. So again, if we look at forecast mode tests of this, again, using 0 to 5 day forecast, time over a 2-month period, you can see there's a lot of green in the left panel, which indicates the difference in clouds between the forecasts. So green is a decrease in low cloud, which is undesirable. On the other hand, if we look at the wind at lead times of 0 to 120 hours, 0 to 5 days of the depth of the atmosphere, see a lot of green, which indicates it's actually improving the wind. So, you get some good things and get some bad things. Okay, so that's the situation we're in right now. Right now we're in the $1,000 funding hiatus, but some work is still going on. Our main short-term focus is implementation of moist EDMF, which we consider to be really one of the centerpieces of our new CPT. So here we try and transport moist conserved variables, the liquid water potential temperature, and the total water mixing ratio, the sum of liquid plus vapor. This requires that we deal with some processes that don't have to be dealt with so carefully right now, stratocumulus, and fragment, merging with our shallow cumulus parameterization in GFS, which increases the challenge but also increases the likely payoff. So the picture below shows an EDMF scheme of work here. So now the eddy-diffusion will go all the way up to the top of stratocumulus, well-mixed stratocumulus layers. The mass-flux scheme will be operative not only in the dry boundary layer, but also in cumulus clouds, as well as in the stratocumulus layer. The JPL version of this scheme uses multiple cumulus plumes with a stochastic internal parameterization, which seems to give good results compared to LES. So just to show you the promise of this approach, this slide, which I got from Joao, shows the implementation of a moist EDMF scheme into a U.S. Navy global forecast model, MAPP. And so in this case, there was a substantial improvement seen when the scheme was implemented in the 500 millibar height anomaly correlation, which is basically a measure of forecast skill. So this is the anomaly correlation in the southern and northern hemispheres from left and right, shown for 0 to 120 hour leads. The perfect would be 1, that's the perfect forecast. Red indicates the control version of the model. As you increase the lead time, the anomaly correlation decreases. And black indicates the model with the moist EDMF scheme added. And you can see that at all forecast leads, you're getting a non-trivial improvement in the skill score, corresponding at 5 days to about an 8-hour increase in the effective forecast skill. So that's a big deal. That's a big change. And in fact, this is now being made operational in the Navy model. So that's the impact we would love to have. I think we recognize already, based on experience, that it's not going to be so easy to have that level of improvement in GFS, but certainly going to try and do what we can. So in conclusion, we're working on this moist EDMF scheme right now to integrate turbulence and cumulus convection. This actually has quite a few similarities, and depending on what level you look at it, the higher order closure approach of the CPT that Steve Kruger is going to define. And in particular, in terms of how you diagnose the model, what kinds of global runs you do, the two groups really probably need to work together, share software infrastructure, have some common meetings. Now, one of the issues is that we are testing this approach in a pure weather forecast mode, which doesn't really favor clouds per se, even though those improvements would be very beneficial to the public forecast system. So I think a discussion about appropriate metrics for moving forward with schemes like this is useful. And lastly, I haven't talked about the GFDL effort because we're awaiting real funding, but the GFDL parallel forecast should expose areas of relative weakness versus strength in the GFS cloud forecast. And we're really looking forward to that, and it'll be really interesting to see how the GFS model does in a more quasi-operational setting in forecasting the clouds. So the goal of that is not to test them as the GFDL as an overall weather forecast model, but specifically to look at the cloud simulations, because clouds develop on fast timescales, and so weather forecasting mode is a good way of evaluating how well your model is predicting clouds. That's it, and I'll take questions.
Thanks, Chris. We have time for one brief question. Any question here in the room for Chris? There is one question that was submitted. I'll just read it out on the chat board from Marjorie McGurrick. Do you have any analyses of decadal differences in 850 millibar zonal winds at latitude bands, such as the horse latitudes, trade winds, etc.?
We have not looked at decadal variability at all in the coupled runs that we did with our past CPT. We did look at long-term climatology in a 50-year coupled run, and so we compared, for instance, the GFS plus MOM to observations, including 50 millibars. We do have those biased statistics, but I don't really think that's really what's being asked for here. So I think the short answer is probably not.
Okay. Yeah. Thanks, Chris, for answering the question and for the presentation. So we're going to move next to Steve Kruger. Steve, are you on the line?
Yes.
We got a little echo here, so let me see. All right, Steve. So I'm going to switch control over to your computer. And you should click that Share My Desktop button.
I did.
Great.
All right. Looks all right?
It's still loading.
All right.
Yep, it looks good. Yeah, go ahead.
All right. Okay. Well, as Chris mentioned, we're the other CPT for improving turbulence and cloud processes in the NCEP global models. And get the right
try clicking once with your mouse on the slide, and I think that'll do it.
Oh, okay. Same thing. Okay. The investigators in our team include both Morthy and Fang-Lin Yang at NCEP, also Robert Pincus, Dave Randall, and Pete Bogenschutz. And I want to reiterate what Chris said. We plan to take advantage of his CPT's previous experience, and we want to collaborate on our efforts for our current CPTs. So I don't really need to say too much about the background for the need of subgrid scale processes. The main thing is that resolutions will be increasing and grid spacings decreasing over the next few years. So this is going to cause basically a problem for parameterizations that have been developed for larger grid spacings and have been tuned for that. And in particular, conventional parameterizations of deep convection in models with grid spacings of many tens of kilometers rely on assumptions that are not consistent with high-resolution models that may partly resolve the deep convection. Shallow clouds will not be even partially resolved in the foreseeable future, so we'll need to continue to parameterize them entirely. And developing parameterizations that work across a range of parameterized and explicitly resolved phenomena is a significant challenge, but that's what we're interested in trying to do. So our goal is to unify how we represent turbulence and subgrid scale cloud processes, and to also unify the representation of deep convection as the resolution decreases. So the first part is on the turbulence part, and this will be complementary to the other NCEP CPT. What we will try out is installing a PDF-based subgrid scale turbulence and cloudiness scheme. This is in the spirit of the work that's been done for CLUB. I'll give you some details on the next slide of how it's a bit different. What this will do, it will replace the boundary layer turbulence scheme, the shallow convection scheme, and the cloud fraction scheme in the NCEP global models. It's for testing, of course. So our scheme is called Simplified Higher Order Closure, or SHOC, and it integrates several existing components. It uses only one additional prognostic equation for the subgrid scale turbulent kinetic energy. This is unlike CLUB, which adds roughly 10. The assumed PDF method of Bolaz et al., which is in CLUB, we use the same exact PDF that's been shown to work quite well. It's a double Gaussian PDF, not PFD. And this is a triple PDF that jointly deals with vertical velocity, liquid water potential temperature, and total water. And we'll use a diagnostic second moment closure this is our simplification, and also a diagnostic closure for the 1/3 moment that we need. And to make up for the simplification, we put a lot of work into developing a turbulence length scale. And we built upon the work of Joao and Jeanette to test a new length scale formulation that has proven to work well in a range of cloud regimes. We've implemented SHOC in a cloud resolving model and tested it extensively against half a dozen or more LAS cases. And perhaps equally importantly, this has also been implemented in a global climate model, and it's one that uses the multi-scale modeling framework, which embeds a 2D CRM. But what this means is that the SHOC is working on a 4-kilometer grid size, which for shallow boundary layer clouds is essentially the same as a much larger grid size because all the circulations are subgrid scale. So I'll just give you a little bit of a view on what we've done. This is work that Pete Bogenschutz has actually done, and these are based on AMIP type simulations. And because we have this embedded cloud resolving model, it can be included in a number of different configurations, just a standard 2D, a small 3D, and a large 3D. And there have also been some preliminary coupled simulations, but I won't show any results from that. For the AMIP type run, just one example is showing the shortwave cloud effects, and down in the lower left is the standard super-parameterized CAM, and it has some deficiencies in the shortwave cloud effects in this transition regime. We should have higher cloud, stronger shortwave effects here and weaker here than are shown. You can see that up here. And with SHOC, we do get an improvement that resembles the observations more. Okay, for the unified parameterization, this is based on recent work by Akio Arakawa, and the idea is to use a unified approach that allows deep convection to cover more than just a small amount of a grid cell. So it can go from anywhere from 0 to 1, and it'll scale continuously between these limits. And what we plan to do is implement this with the conventional parameterization of Chikura and Sugiyama, which includes multiple cloud types, a spectral model, predicts vertical velocity, and is based on a prognostic closure of the mass flux and cloud kinetic energy. So the unified parameterization is basically a method to modify or modulate a conventional parameterization and essentially remove the limitation of small updraft area. Well, with these improvements, we would also like to take advantage of how clouds, radiation, and microphysics interact, because these do interact on the subgrid scale, and we can use information provided by the PDF-based subgrid scale cloud scheme. Here's an example. The cloud scheme may predict a cloud fraction profile like this, and the microphysics schemes may provide profiles of liquid water and ice water like this. For radiation, we can develop synthetic columns to represent the overlap and so on, and the radiation scheme can be applied to these fields of ice water and liquid water content. In this case, I skipped one. Yeah, in this case, we have uniform liquid water and ice water at each level, but you can use the PDF method to provide a distribution of these, which is more realistic, of course, and can help eliminate some of the biases due to the nonlinear aspects of cloud optical depth relations to liquid water content. The radiation in the GFS already uses this method called MIC-ICA, which is an independent column approximation, very efficient computationally. And the nice thing about this is that the extra variability in cloud properties by shock can be included in this with basically no extra expense. Our implementation plan is the pretty much standard one that anyone would be using. We'll first implement them in the NCEP SEM, and this SEM is one place where we're building upon the work of the other CPT. They've provided their single column model version to us, and we'll test, tune, and evaluate the physics modules using ARM data. Very nice cloud and radiation data sets. Then we'll implement them in the forecast model and go through standard procedures evaluating the performance. And as Chris said, perhaps we'll be able to also look at some metrics that will reflect their performance in a climate model, and then implement also in the coupled or the climate model, and do the same thing with the evaluations that we need for climate model runs. And that's my story.
Okay, thanks for the presentation, Steve. Are there any questions for Steve here in the room? Any questions at GFDL on the line? I don't see anything coming through yet through the chat feature, so I'll give it a few more seconds.
Is over.
Right.
We ran over.
All right. Well, thanks again, Steve, and thanks to all the speakers for the presentation today. I thought it was a really interesting webinar, and thanks to everyone for joining on WebEx and here in the room at GFDL, and I guess COLA. There's also a number of attendees at COLA. We have another webinar coming up next month. There is not a date yet for it, but it's going to be on the topic of climate outlooks, so projections, understanding models to interpret projections, and plans for CMIP 6. So we have 3 speakers lined up for that. We're going to hear from Eric Maloney from Colorado State, Justin Sheffield from Princeton, and Ron Stouffer from GFDL. We'll talk a little bit about CMIP 6 plans. So thanks again, everyone, for joining. The recording of this webinar will be up on the website, along with all of the other webinars that we've had over the past 2 years. And you can also download a copy of the slides if you'd like. So thanks. Have a good month, everyone.
Very good. You can end stuff in there. Pilot my rocket ship.